will expand it a little bit so you can see it. All right, so this is what we did last time. I will review it because a review is always good. It helps tremendously every time. Now this low noise amplifier, obviously we want low noise, and always in a low noise amplifier, I have to tell you, you will try to get the highest possible gain for the low noise that has been specified for you. You can never exceed a gain in an amplifier. Now, sometimes people will also give you a maximum gain just in case. I don't know, maybe how the transistor that they will give you to incorporate what characteristics will have. I don't know what later in the system, what kind of other conditions exist or limitations. Sometimes, not all the time, but in few times, they may give you a some other conditions, and they may give you a maximum possible gain. Now, not here, because most of the time they won't. Low noise amplifiers for minimum noise, obviously minimum possible noise, will never have that much gain that you cannot afford. So here they're giving us an FET. All right, these are the characteristics. And they give us the scattering parameters. Obviously, in this particular case, they are the scattering parameters at the design frequency. And how much is the design frequency? 8 gigahertz. For your project or other designs you may have, where you may have a selection of transistors, not just one, then you will have to do a little more work. Because obviously, if you have a selection of transistors, they don't give you one particularly, but they tell you we need a low noise amplifier for this minimum possible noise, and in this particular case for a low VSWR, and then you have to select. Then of course, you have to look at their characteristics, you have to look at the bias, you will have to look at how well your design frequency is situating in the bandwidth of where this transistor performs. You will have to look at the FT to see is it high enough so my transistor works well, all right? So there are a host of kind of other things. But here they've made it easy and they gave us the transistor, they gave us the scattering parameters for 8 gigahertz, and they gave us F minimum, gamma optimum, and R sub n. And usually these three are given by the maker of the transistor. So they will be given to you. Otherwise, if they don't give them to you, then you will have to take the transistor and measure it, which is a totally different thing to do. But I'm just telling you, those are coming out of measurements, unless you have a very complete model that somebody else is gonna run for you. Okay, so they're given to us. Now, what is new, as we said last time in this transistor, is that they have told us that on the front end, you may come from a filter, we said, all right? Normally you will come from a filter to go to an LNA. And you don't want to have very high reflection because that is gonna push your incoming frequency back. It's gonna, your incoming power is gonna be reflected, a good portion of it, and then what is gonna go through the low noise amplifier is gonna be even lower. So it compromises really your optimum design. So you have to have a low VSWR at the input port as it shows there. Okay, now, as we said always, and as I said last time, I will outline those for you. And also I've started populating the part of your eCampus that has the topics, the modules by topics, or it has, yeah, it's not modules by week, there are modules by topic. So, and I will do that so you will, while we'll try to put all of my notes under topics so it's easier for you to find them. So you will have two options. So first thing we do is to check stability of the transistor. Will be nice if it is unconditionally stable. Will also be nice if you can find, as we did last time, whether it's unilateral. All right, I don't have that here, but when we put everything next week, you will see that we will go through all of these tests. So there are a few checks that you have to do up front, important ones. Stability is extremely important because if you don't know which part of the Smith chart is available to you, then you may design a transistor in a place where it's going to oscillate. So if you don't want to do that. So stability is a must. Now, for unilateral, it's only to simplify things for you, because if you can make the assumption, and you remember there was a unilateral value u, coefficient u, that we are calculating, so that 1 over 1 minus u, all of this to the square power, it's less than 1. So if in this case, well, I think it's, no, I don't remember exactly the formula. We are going to go back and see it, but we will have to make sure that this is, that you have an S12 that when you, which is true, yeah, I said the formula that I mentioned was correct. But what unilateral means is that you are going to assume that your S12 is 0. And usually S12's values are always very small, but you cannot always make them 0. Okay, so if you make them 0, if you could make them 0 without impacting the accuracy of your design, then it simplifies a lot of things, as you will see later. But in any case, here we did not do that. We just checked the stability of the transistor, and we checked both K and delta. We said also you have mu. I did not do mu. I did K and delta here. And we found that delta is less than 1, but K is also less than 1. It's supposed to be higher. The magnitude of K is supposed to be higher than 1. And so in this case, unfortunately for us, we understood that the transistor is conditionally stable. The moment you realize that, what do you have to do? You will have to do what next? Who will tell me?
Find the stability regions on the Smith chart?
Exactly. Find the stability region on the Smith chart, which now takes us, remember, that which is kind of interesting on one end. The only thing in a low power, low noise amplifier is like to draw circles. That's all. You draw a circle or circles for everything. You draw circles for input stability and circles for output stability. You draw circles for low noise. You draw circles for gain. You draw for incoming, for the gain of the incoming network G sub S and for G sub N. You draw circles for the whole gain, as you will see here. You draw circles for VSWR. That's all to it, all right? So you always need to remember that if you have to design for something specific, you've got to draw your circles. So you have to find the correct formulas that give you this. So since here we found that it's conditionally stable, we have to find the places for input and output stability. The input stability is given by CSRS, output stability, which is down here. These are the circles. And output stability are those circles. We talked last time how to find them, because in this particular case, those circles were so far out, all right, that we had to think a little more, we had to think differently on how to draw them. But what we find is in this for this particular transistor, we only have two small slivers of the Smith chart where your design may be unstable, which is good news, because you have the rest of the Smith chart, as you can see, for gamma S in the green and for gamma L in the red, where you can select your gamma S, so everywhere outside of the green area, and your gamma L everywhere outside of the red area. Okay, so you know that. Then the next thing, in this particular case, as I said, what I would normally do after stability, I would check for unilateral. I didn't do that here. I don't think even that in this particular case we would be able to consider unilateral, but in any other case, you should try this first before you go to design it regular, like with S1 to non-zero. But in any case, here we did not do that. So we go and we need to design for noise that is as less than 1.5 dBs. Let me, in fact, before go here, we want, well, they say low noise. I selected here, let me put it this way, low noise, and I put here because that's what we've done, F less or equal 1.5 dBs. Okay, if nobody tells you that and you have to go as low as possible, then of course you will see how low can you go from your circles again. You're not gonna avoid that. You're not gonna avoid your circles. Okay, so here we take this, we start with the CSRS here. Okay, we go down here and we go now and develop the circles for the noise. Where are the circles for the noise? Are here. And is this set that gives us those circles. And you remember how we do that? I did a table where you start varying the n values. I don't have n here, but from those you find, from knowing gamma optimum, as you can see here in this case. Here. Knowing gamma optimum and the values of n, you find CF and RF for each one of these values. And of course, from 7, which is this one, you find also what is the corresponding noise value for those. And I have that. I go, since 1.2 is the minimum, I go here to 1.3, 1.5, and then 2. Okay. Now I have those circles, and in fact, I put them here, the blue ones. You see, I have the place for gamma optimum. You see the point, gamma optimum is here. It does not allow me to do that easily. So you see the gamma optimum point, and you see the circle, the smallest one is 1.3 dBs. The other one is 1.5 dBs and 2 dBs. So in fact, the first one, the second one, oops, okay, well, sorry. It moves things and it destroys my designs. Okay, I'm not gonna try to show anything on this, again on the Smith chart. But then you see the 1.3, 1.5, and 2. Okay, so now we got the circles. Then we stop there. All right, we stop, we got the circles. Then what do? Now we've got to talk about the VSWR. And now is where we introduce 2 more reflection coefficients. One reflection coefficient is here, and that's the input reflection coefficient right after the source. And the other reflection coefficient is there. So gamma in super A, so gamma in on the A port, it really shows how much reflection you're gonna come because you're gonna get from your design. Now, why? Obviously, you need to, sometimes you may wonder, you may get confused thinking, well, but we are matching this reflection coefficient at that point, practically, ideally, we would like to match it to the reflection coefficient and the front complex conjugate, but no, we have not done that. We have already deviated from the optimal. The optimal would have been to match the input right after the source and the output right before the load in a complex conjugate way to the source and the load. Well, we are far away from that. Why is that? Because it was important for us to develop the matching networks so that we have stability in the LNA, all right? And so that the LNA operates. Now, to be able to get stability in the LNA and to have the right parameters in terms of gain and so forth, these gamma in alpha and gamma in B are not that important. What we found is that what was important here was the relationship between these two and the relationship between these two. So not exactly up front, but right where the transistor connects to the matching networks. Because these matching networks need to create an appropriate reflection so that the transistor with those reflections and the input port and the output port creates the right amplifier. Without those appropriate reflections there, this transistor is not going to operate. So practically what we do, if you think, is that by introducing this matching network at the front and the matching network at the back, the green and the red, the pink, we are introducing these additional parameters that do a couple of things, a number of things for us. Make the transistor stable, make the gain high, can make the noise low. All right. So by selecting gamma S and gamma L, we achieve those three things: stability, gain, and noise. And this is huge because without having those matching networks, we will not be able to have that kind of control. Okay. However, what happens here is that as we fix gamma S and gamma L, all right, you see gamma S and gamma L, as we fix those things to get our noise the right place, to get our stability and our gain, we destroy the input reflection at the input port and the reflection at the output port. Those go off what they were supposed to be for perfect matching at the input at the output. That doesn't happen anymore. Okay, knowing that we do that, then we come back now to see how well can we match it. Now that we have destroyed the perfect match, that we cannot have a zero reflection coefficient, that gamma in alpha cannot be zero and gamma in beta cannot be zero. Let's see how low can we make it. Is there a way of selecting gamma S and gamma L to do all of these other things, plus give us as low as possible gamma in alpha and gamma in beta? And this is where the VSWR circles come into play. All right. We also said the following, and then you need to remember these formulas here, that if you have this matching network, the green one here, and if you have gamma S here and gamma in here, and in the case where gamma in and gamma S, or gamma in is the complex conjugate of gamma S, then gamma in alpha is going to be zero. However, as we said, since we are taking gamma S for noise, for gain, and for stability, and we have gone away from the perfect match, then of course gamma in alpha is not zero, but this is given by this relationship. Its magnitude is given by this relationship. Okay, if we know so, the magnitude of gamma in alpha from here, then we can find the voltage standing wave ratio, or VSWR, on the front, which is given by this formula. And as I said, in industry, you will never hear about a reflection coefficient at the front. In industry, everything is given in terms of a VSWR. Okay, that's what you're going to get in the specs, 99% of the time. Especially for passive, it's 100% of the time. Okay, so the maker now, the system designer comes to you, and you are designing this low noise amplifier, and the person who is in charge of the system comes and tells you, you know what, I need 1.5 VSWR. Anything more than that is not going to go into the system. So you have to design it for 1.5. Okay, so then what do we do? What we normally do, we go and look for circles. And the VSWR circles for the input port are given by this, where your VSWR in has this formula there. Now, I would like at this point to come here and remind you of a few things. All right. What I would like to remind you, and I have put all of this together a little later, is the following. If you observe the expression for the center of this VSWR circle for the input port, okay, look at this expression. It has in there two things, gamma in alpha, which is given to us from the maximum VSWR, all right? So for example, this circle is gonna give me, I'm not gonna have too many circles in this one, but the one I'm gonna select is going to be this circle that I'm gonna select will correspond to a VSWR of 1.5. And then because I want to be less than 1.5, or at worst, the worst case 1.5, then I know that this circle is going to limit the area from where I can select a gamma S. Okay, so only one circle I need, and this circle is going to be defined by the maximum VSWR. Okay, now what do I have inside here? As I said, if you look at this one, I have the gamma in alpha, which is defined by 1.5 VSWR from this relationship. And then I have also gamma in. Gamma in is in there. It's not gamma S that is in there, it's gamma in. Now, gamma in the optimal case of maximum available gain would have been gamma S complex conjugate, but it's not here anymore, because our gamma S has been selected also for noise and for stability. So the gamma S and the gamma in are not anymore simply related as for maximum gain available. But what are the formulas now that relate these two? The formulas that relate gamma in and gamma S are these two formulas with the following information, that in all of these designs, even if we go off and select gamma S for gain, noise, and whatever else, at the output port, we'll still have this one. So even if noise specifically changes gamma S on the input port, at the output port, our selection will be that gamma L is going to be gamma out complex conjugate. So if this information, like equation 14, is correct as it is, then between the two equations in number 13, you can see that I can find gamma in terms of gamma S. because practically I can substitute gamma out complex conjugate where gamma L is here. And then that is going to give me information about gamma S. All right, so practically you need to remember the following. If you have something like MATLAB, it's going to be easy to do. If you have like a old style calculator, it's going to be kind of difficult. So here I have put the two circles, gamma in and gamma in alpha. Gamma in alpha is given by V's, as you can see, for the maximum VSWR. Gamma in here is given by V's, where gamma L is this. And these are exactly the equations that you have to solve to find the centers, the center position CVI, and the radius. The one thing that you will find quickly is that the phase of CVI is equal to the phase of gamma in complex conjugate. So you have to calculate this here and then. With simple calculations, you can find CVI and RVI. And with this, the circle that we find here is the purple one. Okay, any questions so far? In fact, we can go here, have the same. All right, any questions so far? Okay, so now.
Yeah, this is the kitchen. Pretty messy right now, but whatever. Pretty nice.
Hey man, you aren't muted.
I have one question that's kind of related, but not so much on the exam. Like the iterative method for designing the noise and the gain circles kind of lends itself to MATLAB. But on the exam, will we have a design problem, and could we potentially use MATLAB or?
Yes, of course you could use. I will make sure in the exam, I will not give you something that will be so time consuming. So what I'm gonna ask you to do, you will be able to do whether you can do MATLAB or not. But as I told you, you use whatever tools you have available. All right. If it's easy for you to use MATLAB, you should. If it's easy for you to use another calculator, you should. I'm not going to stop you from doing this. Obviously not. Yeah. Is that did you expect this? I mean, is this clear? Or
yes. Yeah, and really it's more about the exam. And yeah, you said it wouldn't require all the iterations and all the.
No, because those are time consuming.
Right. Thank you.
Yeah. Okay. The next one now, so we found that, all right? We found here the VSWR that if we want, as I said in this particular case, if we want to have a VSWR which is less than 1.5 dBs and a noise which is at most, excuse me, a VSWR which is less than 1.5, not dBs, 1.5, and noise which is less than 1.5 dBs, because this is in dBs. What we said last time is that this is the area you can select from. So from the whole Smith chart, now you narrow it down to something smaller, all right? And now if we add to this a desire to achieve a particular gain, then you're gonna find, then it's gonna take you to the right value of gamma sub S. It's not going to be one unique value, but you're going to go to even a smaller region. That's what I'm trying to tell you. So let's go down now. And it's the same problem as before, but I added to this problem, let me call it 2, just so we don't get confused here. So this second problem is exactly the previous one, but with one additional consideration. And even this additional thing puts you into more trouble in terms of design, all right? My additional request is that I have the maximum possible gain for the lowest possible noise. And unfortunately, that's what we do most of the time. We would like to find the optimum point for that. Maximum possible gain, lowest possible noise. Okay. What I did, as you will do, of course, nobody's going to go and write a huge program to do this on the computer. But what I did was I did say that we made a crude assumption. All right. My crude assumption was GL max is not going to be impacted much by the selection of gamma S. And that's what I did in that solution that I had. And now we remember some things about the gain of the various sections and the total gain. And also we need to remember the definition of the various types of gains, which I have here. First of all, if you know, if you have already designed your amplifier, you know your gamma S, you know your gamma L, then the total gain that you get is the product of these three. So practically, I will write here for you that your total gain, oops, and that's, as you will see later, it's going to be your GP. It's going to be GS, G0, and GL. And if it's in pure number, it's going to be like that. But if you want to do it in dBs, all right, in dBs will be 10 logarithm of GP will be 10 logarithm of GS plus 10 logarithm of G0 plus 10 logarithm of GL. Why I put G? I tell you, if you want to laugh a little bit, you may see that I'm writing and then I change the position of the letters, or in this particular case, I wrote L upside down. I am to say I have this small problem when I write. I had it since I was very, very young, where it's kind of a dyslexia, I think, where I somehow change the order of the letters or the orientation, and then I don't realize that they're different when I do it. I see it later. So just so you know, when you see me correcting a lot of things. In any case, G sub T, let's remember now, we did that as a reminder, the GS here. Now let's do this as a reminder. Let's remember how we defined all the different types of gain. So G sub T is, and I have shown here the power P sub L that goes into the load here. divided by the available by the source at this point. When I say available by the source, what kind of power do I really mean? What condition will specify, what condition this power specifies at the right after the source? Is it not conjugate matching? The available by the source, when we say available by the source or maximum available, sometimes, a lot of times people will remove the maximum available and talk about available by the source. It means that if I had a complex conjugate matching there, then the source could give me this much. All right, but a lot of times it's not this much that goes into the LNA because I don't have complex conjugate matching there. But in any case, in this case, when the ratio between what goes to the load divided by what the source could give, it does not give, but could give, that's called the transducer gain. GP is more realistic. It gives us what goes to the load divided by what goes into the LNA. And why is it that GP is more realistic? Because as I said, we already do not have an optimum matching at the input at the right after the source. We have already altered that by the considerations for minimum noise, for stability, for gain, or a combination of all of those. All right, so GP is really what your amplifier gives. If you were to go to the lab and you were to measure, GP is the real thing to measure because it really tells you how much it goes in and how much is delivered. Then GA is the power available to the load divided by the power available from the source. Again, GA shows like a maximum possibility. If everything were to be ideal, how much really could that gain be? That defines an absolute maximum of the gain. So G sub A and G sub A max, because a lot of times, most of the time are the same with very few exceptions in literature. That's why I have both of them, all right? Those define an absolute maximum to the gain. You can only go down from there. So that's what you need to remember. Okay. Here is how we, from previous lectures, have found G sub T, all right? The two formulas that can give G sub T in one case is a function of gamma S and gamma in plus the scattering parameters in the first case. In the second case is a function, both of them are identical, give identical results, but in the first one you will use the first one if you know gamma S and gamma in, you will use the second one if you know gamma L and gamma L, the second one if you know gamma out, gamma S and gamma L. All right, so if you know gamma in or gamma out, then you use the first or the second. What is G sub P? We said that in the case where gamma in is gamma S complex conjugate, then in reality, gamma P and gamma T are the same as I just discussed before, all right? So that it shows here. Then you have gamma A and gamma A max, all right? So in this case, gamma A and gamma A max is what we already have, which is gamma L equals gamma out complex conjugate, which in our cases we have already. And as I said, these two are identical and some people use them one for another. That's why I wanted to put all of this in case you see them written. And then of course, in all of this, you have S gamma in, given by this formula, gamma out, gamma S, gamma 0, and gamma L. Okay, that is for us to review. Now, what do? I go back and I remember the gain circles. the gains G sub P circle. And the G sub P circle is given by this formula. If you remember, this is a different formula also that has been, that I can give it, I give to you, because in the previous formula, we had the input gain circles for G sub S and the output gain circle for G sub L separately. This formula here, it gives you only one set of circles, which is more convenient, and is for G sub P. So as we did with the G sub S and G sub L circles, we define this small G sub P here, which is the ratio of G sub P to S21 complex conjugate. That's how it has been defined here. S21 is known, we know it. So it's a small G sub P, it's just a ratio. It's just a number. And then we have C sub P given by this, where K and delta are the K and delta will calculate it to see whether the transistor was stable. Okay, so these two. So now instead of using G sub S and G sub L and many more circles, I decided I'm gonna go only with one. And I decided, okay, here just to make it simple, obviously, I decided you could find how much is the maximum possible. All right, so you can find G max. And for this particular transistor was 14.7 dB. So I went there and I said, okay, let's assume that I want to do the 12 dB G sub P circle. Let me use that one instead of using too many and see what I get. When you write this circle here, you find this one exactly, this red one. You see this red one that goes out? Let me just probably, you see this red one? Okay, this one is the G sub P equals 12 dB circle. And what I see here, which is also interesting for this one, is that practically there is almost one point that, now you will say, how did you find this one point? I have to tell you that it was not the first circle that I tried, okay? But so the GP equals 12 dB circle has one point that where it intersects with a 1.5 dB noise circle. Okay, and it happens to be exactly at the fringe of the VSWR. All right, I mean, excuse me, within the VSWR, at the fringe of the noise, 1.5 dB. So I get right at 1.5 dB. I get at 12 dB GP, and then I get lower than 1.5 VSWR. So that will be a nice design point for me. If you could go out and say, now I was able to find this point, and this point, gamma S, which we are looking for, is 0.61 with a phase of minus 139. Then from the formulas I gave you, which are here, from gamma S, I can find gamma out. And from gamma out, complex conjugate, I can find gamma L. Okay? So what I have now here is gamma S, gamma out, and gamma L. And if I know gamma S and gamma L, then what can I do? I can design the input and the output matching networks. And practically, with these two matching networks, I have a low noise amplifier that has a noise of 1.5 dBs, has a gain of 12 dBs and has an input VSWR, which is less than 1.5. And if you were to make it, it would operate that way. Okay. I have not done this because we are going to do the matching networks on Monday. Any questions so far? Was that clear enough? I have uploaded I have a question from Ryan about why did we change GT to GP? Did you understand why, Ryan? Why we got to do GP and not GT? Because we have already, the GP is the more realistic gain we're going to get from this one.
I have another question.
Yes.
So for drawing the lowercase GP circle, how do we find the uppercase GP if it depends on gamma S? Did we just set a value for it and see if we could achieve that? Or
Yes, no, we said 12, I said this lowest, somebody could give it to you, right? In my case, I did more than one GPs. I changed the value of small GP a few times to see exactly what was the highest gain circle that was going closest to the 1.5 dBs noise.
okay, so we pick a GP, draw the circle, and see if it intersects.
Yes,
and we
yes, yeah, exactly. I mean, otherwise it's not possible to do it without checking. We don't know what ahead of time before you have to place them on the Smith chart to see.
Okay, that makes a lot more sense then. Thank you.
Yeah, sure.
When whenever you're doing that though, you were looking for ones that specifically intersected with the noise circles, correct?
Yes, in this particular case.
Yes. So, but let's say if it doesn't necessarily, or I guess it will always intersect, but if it's inside of the circle, then you know that you have noise less than what the circle represents, correct?
It will never be inside. I mean, you mean all of your noise circles to be inside your gain?
No, I mean if the circle for the gain circle, like
yeah, the red one. Yes.
Yes, if it clips inside of one and you choose a gamma S that gives you that point, you would still have a noise less than like the circle that.
Yes. Right? Yeah, you could. Yes. So in noise, if you remember how it goes, your gain circles, how are they going to go? They're gonna go, lower values for gain will go further out. And the G maximum gain is somewhere here, say. That's where somewhere, if I remember, your G maximum, it would be somewhere here. It's not quite accurate, but somewhere there, which means that if I were to get my G maximum like 14.7, that I would need to have much higher noise than 2 dBs. All right, so I'm trying to find the highest possible, because I cannot go further in. I cannot go a bigger, if I go for a bigger red circle than the one I have for 12 dBs, then practically I will go to lower noise, but I will have lower gain. Is that clear? Any other questions?
Yeah, I have one quick question about the homework, if you don't mind.
Not yet. Go ahead.
So it says for problem 1, design an LNA with f equals 1 dB and GT greater than 10 dB. Is that to say we're supposed to have noise of exactly 1 dB and then the maximum gain, or just better than those specs?
So go for the minimum, say, you can do is, could you remind me again, 1 dB noise and how much gain?
Greater than 10 dB gain.
Okay, so I will go for the highest noise and the lowest gain. All right, because any point, so if you go higher than your highest possible, you have failed the design. If you go lower gain than the lowest possible, you're failing the design. So I'm gonna look at what happens, where do these two intersect? If they don't intersect at all, then I cannot solve the problem. If they do intersect and they have a good overlapping, then probably I can do better than just getting 1 dB or 1 dB noise and 10. I can go a little less than 1 dB noise. I can go a little higher than 10 dB. See how I'm thinking?
Okay, I'm just making sure that those are given as specs and it's not like
Yes.
exactly expecting 1 dB noise.
No, I mean, if you can go better than 1, you go, as long as you don't go below 10 dB gain.
Okay, that makes sense. I was just kind of confused by the way
Sure.
the question was posed.
Okay, all right. I have office hours in about half an hour. Okay, so you guys join. All of this information is on eCampus, my notes today. Any other questions?